Team. Welcome back. I'm very excited to announce that we're basically halfway through the semester-ish. I'm not really sure. I did not fact-check that statement. And we are finally moving on from the S to the N in MINS. So, as you might remember, MINS, Mathematics and Nature and Society. We've been talking about society for a long time, but now I kind of want to shift and talk about nature. Still going to be a little bit society-ish. We'll talk about humans, but really this is about the nature of populations, and they can be human, they can be not. So this is really more on the nature side of things. So we're going to talk about linear growth and exponential growth today, and you'll find that these two concepts are very similar to the interest story, the financial stuff. And you might be wondering why we're doing it in this order and it doesn't really make sense. I would argue that it does make sense. I kind of wanted to go into the financial stuff before this because the population growth is a much more rich story in terms of content, I think. And so once we kind of got the financial stuff out of the way, we can start really diving into some interesting math. And so we're doing these two types of growth, and then next time we'll talk about logistic growth, and that will lead us directly into the unit on chaos theory, which is arguably the most informationally rich part of the semester and the most, perhaps also will involve the most struggle, but we'll see. So first of all, I'm just going to jump right into an example here. We're going to talk about linear growth first. Now, thinking about linear growth in populations is really only useful when you're approximating because no population really grows truly linearly. But we can use it to approximate changes over a short period of time. So I'm going to talk about the U.S. population now on the weekly scale or daily scale. Okay, so let's imagine that it's the very beginning of 2016, much simpler times, and we want to approximate how much the population will grow over the next couple days. And so we're going to do this using a model of linear growth. So linear growth, of course, just means we add the same amount every step of the way. And we're going to do this on the daily scale, so it'll be every day the same amount gets added. And so we need to figure out what this rate is, first of all. So according to the U.S. Census Bureau, we can kind of approximate the number of people that get added to the population every day. And so the U.S. Census Bureau in 2016 approximated a couple factors that contribute to the change in population. They first say that we need to account for one birth, so one person being born every 8 seconds. And then we have to account for one death every 11 seconds. So we'll do minus one person for 11 seconds. And then we have to account for another person who is an international immigrant every 29 seconds. So one person's born every 8 seconds, one person dies every 11 seconds, and one person enters the country every 29 seconds. And now just to add these together, we just need to come up with common denominators for all of them. And a good one for these leads us to the following answer. We have that we have a net gain of one person every 15 seconds. And I know this because I'm a math grad student, and in math grad school, you really don't do anything apart from adding fractions. And this is roughly equal to about 6,000 people per day. So 6,000 people get added every day. And now let's go ahead and look at how that affects over the first few days of a single year, how that affects the population size. So I'm going to set up a little table here. We'll have day of year, and we'll have population. So we'll start at day 1. Actually, we'll start at day 0. Let's call the first day day 0. And let's say that on this day, and this is population in thousands of people. Let's say that on the first day, day 0, there are 322,762,000 people. So this is actually this many plus. If you did this in people, there would be 3 more zeros, but we're doing this in thousands of people. Okay, great. Now let's move on to day 1. So now we just add this 6,000. So we have 3, 2, 2 again, 7, 6, 8, and then 3, 2, 2, 7, 7, 4, 3, 2, 2, 7, 80, and 3, 2, 2, 7, 86. And okay, that's enough of that. So this is the first. So day 1, day 2, day 3, day 4. So first 5 days of 2016 give us this population roughly for each day. Okay, so now let's say that what we want to do is, I'm just going to put that rate back up here somewhere so I don't forget. Let's say we want to add up all these numbers. And it's pretty easy to just add up 5 numbers, of course. But if we imagine that this went all the way out really far, then it would be a lot harder to just add a bunch of numbers over and over again, and I would want an easier formula for that. But first, let's just consider these 5 numbers, and let's say that we want to add them all, because we want some motivation for this, right? So these are people living in a country, and if we know how much food a person needs per day, then we can use the sum of the number of people every day to give us an estimation for the amount of food that our country needs to adequately feed its citizens for a certain period. So that's one possible reason that we would want to add the population of every day together. So if we're summing up this population, then this is of course just equal to all of these things. So, and then I'm just going to leave out the 322 and just look at the thousands because the 322 is the same. So we can just keep in mind that we'll add 322,000 to this when we're done. But adding up just these last 3, the hundreds place of all these, we would have 600, 670 or 762 plus 768 plus 774 plus 780 plus 786. And again, like I mentioned, we can just do this, but there's a trick that I want to demonstrate here. And to do that, I'm going to rewrite this sum in the backwards order. So S equals, once again, this is the exact same, this will be the exact same sum, but I'll say it's equal to 786 plus 780 plus 774 plus 768 plus 762. Okay, so that's cool. Now, let's double up that sum, so 2s. And notice that we'll get 2s from adding these two numbers up for each column. So let's add the first term to the last term, and then the second term to the second to last term, and so on to each of these. And so the first set of terms, I'm just going to open up my calculator here. If it works, come on phone. All right. Okay, so first let's do 762 plus 786, and that's equal to 1,548. And I'm going to try to write that a little bit skinnier so that it fits directly under the 2. 1,548. Okay, and now let's go ahead and try that with these two. 768 plus 780. Oh geez, it's the same thing. And why is that? Well, every time we move forward, the top number gets bigger by 6, the bottom number gets smaller by 6. So these will always be the same. They'll always be equal to 1,548. Okay, great. So that's really convenient, that if we get 2s, to get 2s, all we need to do is add the first term to the last term, and then add that n times, in this case 5 times. So 1,548, 2 for 5, there are 5 of them. So this is equal to 7,740. And so s is just equal to 2s over 2, of course. So that number divided by 2 is 3,870. So what we've done here is we've figured out s really only using information from the first and last term. And so this actually brings us to the arithmetic sum formula. So this type of sequence is called an arithmetic sequence. You don't have to remember this, but that's what it's called when you're just adding the same amount each time. And the sum is just equal to the first term plus the last term. So remember, the last term was the last population was population of day 4, and there were 5 days total. So this is, the last term is denoted by Pn minus 1 times n, so times the number of terms, divided by 2. So this top piece is 2s, and it came from first term plus last term multiplied by the number of terms that there are, and then we just divide by 2. And so this is a very useful formula, and you'll have to use it a handful of times. I'll always give it to you so you won't have to remember it, but that's where it comes from. Okay, so one last thing I want to mention here is that the formula for the population at any given time is going to be equal to this. So P at some time t is equal to P0 times 1 plus rate times time, just like for interest. But now R is equal to 6 for that 6,000 divided by the starting population, which was 322,662. So this would be our R, and then so if we wanted to get the time at any, or the population at any given day, we would just plug in the number day as t, and that would get us there. Okay, so linear growth, relatively simple, and also useful mostly for approximations. Really all of these are useful for approximations, but linear growth is simple and is limited because of how simple it is. So now I want to move on and talk about exponential growth, and so we'll do that now. And really with both linear and exponential, this is always growth or decay, where decay is just negative growth. So you can think of this as growth or decay. So the example that I'm going to give right now is really more of decay or a negative growth example. So example, this is going to be virus eradication. So we've got that, this virus that we call the gamma virus, and that gamma virus has a population, P0, of 1 million. But because modern science comes up with this new vaccine, and we've got good health policy, I hope, we have that this the population of this virus is actually decreasing by 70% every year. So we've got R equals negative 70% or minus 0.7. So you can also think of this as the population at any time after any year is down to 30% of what it was the previous year. So 70% of it gets subtracted off. So the way this looks is if we have year and then number of cases. So by population of the virus, I really mean the number of cases. Then we have 2015. And so first it's 1 million, and then it's 300,000. So we subtracted off 70% of that original 1 million. And now we're going to do that again, be 90 million, and then 27 million after that, or sorry, I keep saying million, really, 90,000, 300,000, 90,000, 27,000. This is for 2016, 2017, and 2018. And then projecting forward, continuing to project forward. So this, we'll say that this example was made up in 2015, so these years hadn't happened yet. In the year 2025, we should have 6 cases. In the year 2026, we should have 2 cases. So this, on a graph as a function of time, this will be asymptotically approaching 0. And this is what exponential decay looks like. And so let's imagine that, given the fact that we can give, let's say that the vaccine in question that is being used to eradicate this disease needs to be given annually to every person who is exhibiting symptoms of the virus, then the number of vaccines we would need over these 11 years is the sum of all these numbers, because every year we would need 1 vaccine for every person who has the disease that year. And so the number of vaccines we would need is the sum of all these numbers. That brings us to the sum formula for this type of model. And so first of all, so I'm going to put a little section here for formulas. And so the first thing I want to mention is that this, the population at some time t is of course given by p, the original population, times 1 plus r, and then raised to the t. So this is very similar to the compound interest thing. And this comes from the compounding of that rate change. So the sum, and this is called the geometric sum formula. This is equal to r raised to the n being the, in this case, number of years, minus 1 times the original population divided by r minus 1. And for the arithmetic sum formula, I was able to give you kind of a logical explanation for it, and I can't really do that here, not without taking way too much time and losing almost all of you in the process. So I'm just going to provide it. This is equal to s, and now I'm going to apply it to this case here. So here we would have that it's equal to so I made a quick mistake here. This should be big R, so not little r. So this was little r was negative 0.7. And R, big R, is equal to 1 minus 0.7, or 0.3. So that's the important piece there. It's 1 big R is equal to 1 plus little r. Okay, so with that, moving forward, this is going to be equal to 0.3, then raised to the, let's say we're doing this over 12 years, so say we're doing this over 12 years, so we'll do 0.3 raised to the 12 minus 1, then times 1 million over 0.3 minus 1. And then this is equal to 428,571. And so these are the number of vaccines that are needed. Okay, so in class we'll go through some more fun with exponential and linear growth and see how these things can be applied in different ways. And then for Thursday, we'll be moving on to logistic growth, which is a whole nother beast in itself, and we'll have a lot of fun with that. Okay, thanks for viewing, and I'll see you later.